Every time you open an app, you face thousands of options. To prevent information overload, platforms rely on algorithms to decide what appears. The mathematical goal for this filtering is estimating utility, expressed as the function arn of u, I. This formula attempts to predict the specific evaluation, or rating, the user, u, will assign to an item, I. Early developers focused on predictive accuracy by aiming to minimize root mean square error, or RMSE. RMSE is a standard statistical metric that measures the average distance between a system's predicted ratings and the actual ratings given by users in offline testing. The 2006 Netflix Prize formalized this approach. By offering $1 million to improve their recommendation accuracy, the competition standardized the industry's view of algorithms as a static matrix factorization challenge driven by explicit historical ratings. But perfecting historical rating predictions fails to capture how human beings actually behave on a live, dynamic platform. Relying on explicit data, like 5-star reviews, introduces a structural flaw: extreme sparsity. The vast majority of users will never explicitly rate the vast majority of items they consume. To solve this, modern platforms replace star ratings with continuous streams of implicit behavioral feedback. Every click, hover, and pause is tracked. This shift requires the processing of unary ratings. Unary data consists of only positive interactions. An action registers as a positive signal, while the lack of an action registers as missing data. This creates the absence of interaction challenge. A missing data point doesn't always indicate a dislike. It often means the user hasn't discovered the item yet, and the algorithm must differentiate between a true rejection and an unseen opportunity. Social media buttons turned explicit user actions into high-frequency behavioral signals. A single like provides a visible endorsement that doubles as a data point for continuous passive tracking. Architecting a production recommender system means abandoning the static matrix. The goal now is synthesizing endless behavioral noise into actionable user intent. There are two primary algorithmic pathways to process this intent. The first is collaborative filtering. This method correlates users based on their behavioral overlap. If two users click the same sequence of links, the system links their profiles, ignoring what the actual items are. Advanced implementations use latent factor models like singular value decomposition, or SVD. SVD is a mathematical technique that reduces the massive user item matrix into a lower dimensional space, forcing users and items to align along invisible conceptual axes based on implied preferences. Collaborative filtering suffers from the cold start limitation. It cannot recommend brand new items because they lack behavioral history. To fix this, platforms use content-based filtering, which extracts semantic features directly from the items themselves. This requires semantic indexing. Engineers use endogenous indexing to map the distribution of keywords within an item's text, and exogenous indexing to map items against external databases like knowledge graphs to resolve synonyms in context. Today, deep learning architectures process unstructured media. Convolutional and recurrent neural networks, systems designed to analyze grid-like data such as images and sequential data like text, are deployed to compress raw audio, video, and natural language into dense feature vectors. A resilient modern system fuses collaborative crowd wisdom with deep learning content awareness, ensuring accurate recommendations across massive, constantly updating tau logs. But the RU baseline assumes preferences are static. In reality, user tastes are dynamic. They degrade, shift, and react based on the immediate situation. Context-aware systems inject variables like time, the local weather, and physical location into the math. Engineers apply this through pre-filtering the raw data before prediction, post-filtering the recommendations after prediction, or directly modeling the context into the algorithm. The extreme edge case of this shift is session-based recommender systems. The user is anonymous. The system has zero historical profile data to draw from. Session algorithms must predict immediate, sequential user intent based solely on the short-time temporal dynamics of the clicks happening in that exact moment. In modern mobile environments, capturing when and where a user is making a choice is often a better predictor than knowing exactly who they are. The architecture expands further when the standard single-user utility function breaks down. People-to-people reciprocal recommenders, used in dating apps and job matching platforms, must simultaneously satisfy the utility thresholds of two independent agents. Both parties have to agree for the recommendation to succeed. Group recommender systems face a different mathematical challenge. The algorithm must aggregate competing individual preference models into a single sequence of items that satisfies an entire room of people. Expanding these architectures into social and professional domains requires the system to act as a diplomatic mediator, balancing the utility of multiple participants simultaneously. This radar chart illustrates the tension in algorithmic architecture, balancing three stakeholders. Consumers seek discovery, providers demand exposure, and platform owners require conversion. Optimizing purely for accuracy causes blockbuster bias. Recommending only universally popular items creates an echo chamber, starving niche providers. The commercial reality of this math is massive. Slight algorithmic tweaks in conversion optimization dictate the physical movement of millions of items worldwide. Achieving perfect predictive accuracy in a vacuum is a technical victory, but a systemic failure. It destroys the long-term diversity and economic health of a multi-stakeholder platform. Because of this, offline precision metrics are insufficient. Modern platforms rely on multidimensional evaluation frameworks deployed in live A/B testing environments. These frameworks measure novelty, which tracks the discovery value of an item, diversity, ensuring broad catalog exploration, and fairness, which quantifies bias mitigation across different provider groups. This is vital in public service models, where the primary stakeholder goal is diverse, fair information dissemination rather than direct sales. The final layer of the architecture is human-computer interaction. The most accurate mathematical prediction is useless if the user's cognitive process rejects it. Explainability must be built directly into the UI. Transparent justifications for why an item was recommended establish trust and actively aid the user's decision-making process. The modern recommender system functions as the primary digital architecture dictating the landscape of human choice.